In this video, I would like to present a research and development based economic growth model that includes automation and analyzes the effects of automation on long run economic growth and on inequality. This is based on the article Innovation, Automation and Inequality, Policy Challenges in the Race Against the Machine, published in the Journal of Monetary Economics in 2020. We have already seen in previous videos that automation became important, particularly over the last decades. So here we again see the worldwide stock of operative industrial robots from the 1970s onwards, and it was rather negligible until most of the 1980s. Then growth increased, but it was still sluggish, and only after the global financial crisis in 2008, growth in the stock of industrial robots took off, and now we have projected 4 million operative units in the year 2021, basically. Now here we see a distribution of the worldwide operative industrial robots in terms of the robot density. So that's the number of industrial robots per manufacturing worker or per 1,000 manufacturing workers. And the darker a country's color is, the higher is this number, and the lighter country's color is, the lower is this number. And we have many countries with no data, but that correlates quite strongly with having a low number of industrial robots, basically. So what we see here is that the robot density tends to be highest in high-income countries and also in countries where the population is aging rather quickly, because in these countries the workforce might be shrinking, and therefore automation might be one of the strategies to cope with a shrinking workforce. So we see that particularly in countries like Germany, Italy, Japan and South Korea, the robot density is rather high, and it is comparatively lower in the United States or in the UK, because these countries tend to have higher growth rates of the population, sometimes due to high inward migration, for example in the UK from Eastern European countries over the last decade. And that means that these countries tend to have higher robot densities. And the robot density tends to be lower in countries with high population growth, or where the wages are rather low, so where we have low income countries, particularly Southern America, Africa, and many parts of Asia. Now, China is particularly interesting because they saw quite fast growth in the stock of industrial robots lately, but nevertheless, due to the large workforce, the robot density itself is still comparatively low. So overall, this depiction might already hint towards the fact that automation is particularly important for those countries that are on the research frontier, where innovation is going on and so forth. And we know already from endogenous and semi-endogenous growth theory that economic growth in these countries is particularly well described by these endogenous growth theories, where research and development and innovation is endogenously explained within the model itself. And these frameworks have predictions that align quite well with some of the stylized facts. So innovation-driven growth theory can explain why these countries have been growing in the long run and why there is higher labor income in these countries, and so on and so forth. However, these models still have problems to explain some of the stylized facts that we saw particularly over the last decades in many of the rich countries. Namely, that particularly the wages of people with higher incomes and probably higher education have been growing, but those of people with lower education levels have rather stagnated or even gone down a bit. So we have seen wage polarization and rising income inequality, and the basic R&D-based growth models that we considered so far are based on the representative agent framework, and as we already discussed in the chapter that dealt with economic modeling, that is an assumption that might be quite well suited to considerations of factors that are not related to inequality. But of course, if we assume a representative agent, we cannot really analyze inequality dynamics. So we need a different framework in this case. Then these models have also not explained the declining labor income share that we have observed since the 1970s and 1980s, although some automation augmented solo models or OLG models can explain this. These models have not explained rising wealth inequality, the fact that wealth of the richer parts of the population grow faster than wealth of the poorer parts, where wealth of the poorer parts mostly stagnates or even declines in reality. Then these models also cannot explain that educational attainment over the last decades has increased. We will try to explain this by having endogenous education decisions. And finally, we also want to say something on the issue of technological unemployment, because potentially that's one of the fears related to automation, that it might lead to technological unemployment. And we want to analyze one extension of the model that can deal with technological unemployment. So overall, our aim is to build a research and development based growth model in this chapter that includes automation and can explain the stylized facts 1 to 6, so it can add to the research and development based growth literature issues related to inequality dynamics, declining labor income share, wealth inequality, and educational attainment and technological unemployment. Now, the basic model structure is that we assume an overlapping generations economy where individuals live for 3 time periods. In youth, they receive a basic level of education, but they do not make any economic decisions, so they receive consumption and so on from their parents. Only when entering working age, the economic decisions are made, and the main decision of workers at that age is the consumption savings choice, of course, but in addition, the choice of whether or not to upgrade the skills, so whether or not to go to college to obtain higher education. People can choose not to upgrade their skills and remain low skilled with a basic education, but in exchange they can start working immediately and earn a wage income, or otherwise they can choose to go to a college or university and upgrade their skills, but for that they forego wage income, and there is a certain effort that they have to undertake in order to obtain a college degree, about which we will talk later. And then the third phase in the individual life cycle is retirement. So after the working age, people retire and have to live out of their savings that they accumulated during their working ages. And now, based on this structure, we have 2 types of workers. Those who chose to obtain a college degree become high skilled. They perform tasks that are not that routine and therefore difficult to automate. And these workers are rather complements to machines and not so much substitutes for machines. And we have the L types. These are the low-skilled workers. They chose to remain without a college degree and just have basic education. They are more performing routine tasks. For example, think about people working on an assembly line and performing the same production steps. And therefore, they are easy to automate and they are substitutes for machines. Based on this structure, we have 3 production factors. The L-type workers, and we assume that they can only be employed in final goods production, so they are manufacturing workers and they work, so to say, on the assembly line. Then we have H-type workers, the high-skilled workers, and they can be employed either in goods production, but there they would be engineers, or in research and development. And in research and development, they would be the scientists that develop the new blueprints, the new ideas, and they drive innovation. And then we have physical capital in the form of the machines and robots in a model that can replace the low-skilled workers easier than they can replace the high-skilled workers. In this version here, we treat the population size and the workforce as given, but the results are robust to having population growth at a positive rate n, except for the fact that in these cases we would have to choose the parameter values a little bit differently when we calibrate the model, basically. From the household side, we conceptualize the trade-offs by introducing a utility function where consumption increases utility in a logarithmic way. So we again have the simplification of a logarithmic utility function where income and substitution effects cancel out. So utility increases in consumption the period of life when people are workers. It increases in consumption the period when people are retirees, and here they consume their savings multiplied with the gross interest rate, which is given at the world level according to our assumptions. So we assume that the interest rate is determined exogenously in this model. Not much would change if we have an endogenous interest rate, except for the fact that most of the dynamics become much more complicated. Again, future utility is discounted with the discount factor beta. And now the new element is that education or higher education, obtaining a college degree, entails effort, and this effort reduces utility. Now we assume that there is a certain function by which it reduces utility that depends negatively on the ability of a person. So if a person has higher ability, then she finds it easier to obtain a college degree. So that reduces effort and therefore the utility cost of higher education. And the second cost of education is basically the time that one has to put into obtaining a college degree, and we denote this share of total available time as eta tilde. Now, strictly, this does not need to be part of the utility function. It's part of the budget constraint, but we just write it here to show that this is the second cost of education that shows up. Now, the budget constraint, here we assume that there is a tax rate tau w on wage income. In the basic version of the model, that will be equal to 0. But for the simulations later on, we assume that wage tax is one of the possibilities of how we can finance redistributions to the those parts of the population that might be affected negatively by automation. Then eta, as I said before, eta tilde is the fraction of time that a college degree takes out of the period of life when people supply their work on the labor market. So the time that they can spend on the labor market is 1 minus eta tilde. So that would then be the factor with which we have to multiply the wage rate in the economy. And this wage rate is type dependent. So we have two types, J, those with low skills and those with high skills, and the wages of those with low skills would be lower, but in exchange they would have the full available time in the period of life when they supply their work on the labor market for earning wage income. And for the high skilled workers, the wages will be higher, but in exchange, as a cost, as an opportunity cost, basically, they have to spend a certain fraction of their time not working, which reduces income. Then we have a transfer that is type dependent actually, which can be used to model redistribution. And now the total income consists of wage income plus transfers, can be used for consumption or saving. And the solution is basically straightforward, can be obtained by standard application of the Lagrange procedure. Would be that consumption depends positively on income in the period of life when people supply their work on the labor market, and the same holds true for saving. However, now consumption depends negatively in the first period on the discount factor, which is reasonable because if people become more patient, they would shift consumption to the second period. So that would mean that they would save more. So a higher beta induces higher saving. This decision so far was straightforward and the standard decision that individuals make in such an overlapping generations model. But the second decision, the education decision, might be a little bit more uncommon. And that is, individuals need to decide whether or not to obtain a college degree. Now, there are two costs of education, as I said before. First of all, people have to put some effort into this, which comes with a utility cost, and they have to forego wage income. Now we assume that learning ability A is distributed in the interval from 0 to 1 in kind of a truncated normal distribution or something like that. So like the IQ, which is by construction normally distributed. And then we assume that there exists a pole for ability. such that if ability approaches this pole, the effort cost of education increases and goes to infinity. So that is to say, in other words, that there is a certain ability threshold, and for people below this ability threshold, it's just not possible to obtain a college degree, at least given that we have a finite time available for the college degree. Well, and then in this situation, individuals will invest in higher education if the additional wage that they get by the higher wages over their life cycle, already taking into account the opportunity cost in terms of time of higher education, is able to overcompensate them for their utility loss due to effort. So that is to say that additional income buys utility via higher consumption in the period when people are working and in the period when people are retiring. So we have one plus beta here. So we have the higher income then in the utility function. So that's why we have the logarithm here, and we have two periods. So that additional income has to be that the utility that people can buy with this additional income has to be higher than the utility loss of obtaining a college degree. And we denote this threshold income or threshold indirect utility level by W tilde. Now we can depict the solution of the education problem by means of a simple graph where we plot the skill premium W on the horizontal axis and the share of the population that chooses not to obtain a college degree on the vertical axis. And that depends on the ability level. So if the skill premium is 0, there is no incentive whatsoever for people to obtain a college degree. So the total share of the population, 1, would remain unskilled. Now, as the skill premium increases, a larger and larger share of the population obtains a college degree. For example, for this W tilde, 1 minus A star would obtain a college degree, the share 1 minus A star, and the share from A star to 0, or share A star basically, would choose not to obtain a college degree. And now, if the skill premium increases further, that would mean that ever more of the people with lower ability levels also start to invest in education. The first to invest in higher education would be the ones with the highest ability levels. But then, as the skill premium increases further, there is a pole towards which this function converges, and people with ability levels below A bar would not obtain a college degree because the effort costs are just too high compared with the available time that these people have in the working life. So in the long run, if the economy grows and the skill premium grows, the share of the population obtaining a college degree would converge to 1 minus A bar. Now we come to the production side of the model, and here we again assume a final goods production function that is Cobb-Douglas, where we have the high-skilled workers. These are the engineers in the final goods sector with an output elasticity of 1 minus alpha. They work with the robots and machines with an output elasticity alpha. There is not just one machine variety, but there are as many as there are blueprints in the economy. So we have to take the sum from blueprint 1 up to the latest developed blueprint, AT, to have the total stock of capital in the economy in terms of machines and robots. So that's fairly the standard part. What's not so standard is that we now have also the low-skilled workers, the assembly line workers, with the same output elasticity alpha as robots and machines. So what this implies is that these workers are easier to substitute by the machines than the engineers. So engineers and machines are to some extent complements and are both needed, but the assembly line workers are more substitutes to the machines, and they can be replaced by the machines or robots. Now, what does this imply for the factor rewards? The wages of high-skilled workers are the marginal product or marginal value product, but the final goods price is normalized to 1 of high-skilled workers. So it's the derivative of the production function with respect to LH. Now, if we take this derivative, 1 minus alpha comes down from the exponent is reduced by 1, so we have LH to the power of minus alpha here, and the term in parentheses stays unchanged. So now this can be rewritten as just 1 minus alpha times final output divided by the low skilled, the high skilled workers employed in the final goods sector. Now we see the wage rate of high skilled workers increases with GDP. So if GDP increases because of technological progress, this also raises the wages of high skilled workers. As we see next, however, this does not hold true for the wages of low skilled workers. The wages of low skilled workers are again the marginal value product of low skilled workers, so the derivative of the production function with respect to the low skilled labor employment in the final goods sector. And if we take this derivative, what we get is actually alpha times the ratio of high skilled to low skilled workers to the power of 1 minus alpha. So now here we don't have GDP and we don't have the level of technologies here. So we see basically that technological progress per se does not increase the wages of low skilled workers, it only increases the wages of high skilled workers. And as we will see later on, that drives a wedge between the wages and can explain rising inequality to some extent. However, as we will also see later on, the fraction of high-skilled workers in the population is endogenous because this is a choice based on the education choice. So we could have, during the transition to the long-run equilibrium, at which a share 1 minus a bar of the total population will have obtained a college degree, during this transition, we still have that high-skilled workers become more in the economy. So some low-skilled workers choose to become high-skilled. And if this is the case, then the denominator here would decrease and the numerator would increase, which means that the wages of low-skilled workers could still grow for a while until no low-skilled workers, no additional low-skilled workers choose to become high-skilled anymore. So in the very long run, when the education threshold, the ability threshold is reached and no additional people obtain a college degree irrespective of an increasing skill premium, then the wages of low-skilled workers would stay constant. And then we also have the price of robots and machines, so the inverse demand function basically, which is the derivative of output with respect to machine input for the variety xi. So if we take this derivative, we get this expression here, but now we introduce also a second tax into the model that we will analyze later on, and that's a robot tax. So we assume that, so in the basic model, the robot tax is 0, but later on for each robot that a firm buys, it has to pay a tax tau r. Now the important takeaway here from this slide is that innovation increases the marginal product of high-skilled workers, so it increases high-skilled wages, but it leaves ceteris paribus, as long as the ratio of low-skilled to high-skilled workers doesn't change, it leaves the wage of low-skilled workers unchanged. Now, what about the research and development sector? We model this as in the semi-endogenous growth framework that we discussed of Jones, so that new blueprints are produced according to the research production function that we have here. When new blueprints between time t and time t plus 1 is the difference in the stock of blueprints at time t plus 1 and the stock of blueprints at time t, so that new blueprints determined in the period from t to t plus 1. That depends positively on the number of researchers employed, and that's the second type of high-skilled labor in the economy, the scientists in the research sector, so LHA now. And these scientists have a productivity delta bar, and this delta bar depends now again on the inherent productivity of scientists, delta, the intertemporal knowledge spillovers AT to the power of phi. So phi again measures the strength of intertemporal knowledge spillovers, where we assume this to be smaller than 1, as in the Jones model. And we again have the stepping on toes externality, that the number of researchers, the more researchers we have, the likelier it is that they develop the same idea. So lambda again being an indicator of the strength of this stepping on toes externality, here in this case, as in the semi-endogenous growth model. An inverse measure of the strength of this stepping on toes externality. Now, when we solve for the growth rate of technologies, then we get this expression here, as in the Jones model. So the growth rate would decrease in the stock of already accumulated blueprints because we have these weaker intertemporal knowledge spillovers that sterilize the strong scale effects. So we would have a weak scale effect in this sense in the model. Now the profits in research would be the new patents that are produced by the representative firm, so this part here, times the price of the blueprints that such a firm can charge. So that's the revenue of such a firm. And we have to subtract the costs of production, which is the wages that they have to pay to the scientists that develop the new blueprints. And what we assume here in the background is that a patent lasts for one generation. That would be approximately 25 years or so. And that's rather well in line with the standard patent length that we have in reality. For example, in the United States Patent and Trademark Office, the patent duration would be about 20 years. Now, for the intermediate goods sector, we assume that the central variable production input factor is physical capital. So these firms transform physical capital into the machines and robots. The operating profits of such an intermediate goods producer would be the price that they can charge for the machines multiplied by the amount of machines they sell. And the price itself depends on the number of machines that they sell because we will have monopolistic competition due to the patent system. So that's the revenue that these firms earn. And the costs for production are what they have to pay for the capital that they rent, and that's the exogenously given constant capital rental rate. Now, depending on the structure that we had previously, where patent duration was one generation, we have two types of firms. Those that produce the old vintages, where there is no patent protection anymore, and these firms perform marginal cost pricing. So the price that they charge for their machines is equal to the cost in terms of capital, so R bar. But there are also those firms that produce the newest vintages that are patent protected, for which these firms have obtained a patent and are therefore the exclusive producers of these machines or robots. Now they perform markup pricing. So the price that they charge will be a markup over marginal cost, and we can basically perform all these calculations there, plug all in and so on. And what we would get in the end is that the markup is 1 over alpha, which is greater than 1. So these firms would charge a price that is higher than the marginal cost R bar. Now the profit of these firms basically has to be equal to the price of the blueprint, because they use their operating profits to purchase the blueprint from the research and development sector. And therefore, if the price of the patent was lower than the operating profit, there would be an incentive for firms to enter intermediate goods production, because there would have been overall profits to make. So there would be firm entry so long until, again, the price of the blueprints would be equal to operating profits. And by contrast, if the price for patents was higher than operating profits, then firms in the intermediate goods sector would make losses. So there would be shutdown of firms and so on, firm closures. And then in the end, this would last again so long until the price of blueprints is again equal to the operating profits. Now, overall, what we can show is that the output of the firms that produce older vintages is, of course, higher than the output of firms of newer vintages, because they perform marginal cost pricing, so there is no monopolistic competition anymore. And the factor by which it is higher is alpha to the power of 1 over 1 minus alpha. Now we can use this insight for performing aggregation. So to perform aggregation and compute the number of robots that we have in the economy, we would have to sum over all the old vintages, xj, from the first patent, the oldest patent in the economy, up to the stock of patents at time t minus 1. Plus then we have to sum over the new vintages, xi, from the stock of patents in the previous period up to now. And what we would get is a tilde, actually, which would be the multiplier of the number of machines in the aggregate production function in equilibrium. And this is computed as we have it here, so that we multiply the old vintages by something that is greater than 1 here in this part. and we add the new vintages basically here and multiply this by the number, by the machines of the new vintages, and then we get the aggregate production function where we can substitute out the sum basically. Now we can in principle solve the economy. Once we know the number of scientists, we can compute from this the growth rate in the stock of technologies, and from that we could compute the wages of high-skilled workers and wages of low-skilled workers, how they evolve and so on and so forth. The problem is that there is kind of an interdependence between this growth rate and the wage gap and the number of people who choose to become high-skilled, which in turn determines to some extent the number of people that work in the research and development sector. So we have kind of a circularity there that we have to solve, and that is not present in the standard endogenous growth model of Roma, where the solution can be obtained in an easier manner. However, what we need first is the market clearing on the labor market. So that means that the total amount of high-skilled labor that is available in the economy has to be either employed in the final goods sector or in the research and development sector for labor market clearing. So all high-skilled workers are either engineers working in production or scientists working in research and development. And the wages of the scientists and the engineers equalize in equilibrium. Otherwise, if one of the two were higher, then people would only want to be this kind of worker and not the other one where wages are lower in equilibrium. We can plug all in and derive an implicit solution actually for labor employed in research and development. This implicit solution is given here, and that's exactly one of the differences to the standard Roma model, because in the standard Roma model we can solve for the labor employment in research and development explicitly. So then we would have it and we can plug it in and solve the rest of the model equations. Here, however, this is only implicitly given, and it still depends on the overall number of people who choose to become high-skilled. But this is a choice in the model, so an endogenous choice. So we have this circularity that we cannot solve this analytically, at least not for the transition period. So for a given number of high-skilled workers, this would be an implicit solution in one unknown, and we could in principle solve it implicitly for the number of researchers in the R&D sector. And from then, everything else can be solved recursively. At the steady state, in the long run, when we reached the situation when the ability threshold is reached such that no additional people choose to become high-skilled, even if the skill premium increases, in this situation, we can indeed compute the results analytically. However, during the transition, as long as the overall number of high-skilled people changes, we only can provide numerical solutions, which we will do later on.